When multiple elements combine to form a compound, we need to keep in mind the fact that each of those elements has its own unique atomic mass. And so each one of those elements is going to contribute a different percentage of the total mass for the entire compound. And these percentages can be useful to identify because they are an absolute ratio of the elements one to another in that given compound. And it's a unique combination of percentages. Obviously, we hope that they all add up to 100%, but because it doesn't matter whether we have a small amount of that compound or a large amount of that compound, the breakdown of the elements that make it up and that ratio is consistent, and therefore the percentages will be consistent, and therefore the percentages can be used to help identify the formula of a compound in certain instances. In order to calculate the percent composition for a compound, the first thing that needs to be done is to determine the total mass of each individual element that is present. And we already do this to an extent when we're calculating the formula mass, which actually will be a component of this problem-solving process. But what's different here is that we will actually not only be isolating that total mass of the entire compound, that formula mass, but also calculating each individual element's total atomic mass present in that compound. And so to do that, you take the atomic mass to 3 sig figs from a periodic table, multiply it by whatever subscript it may have. If there is none, then it's just 1. And then again, you determine the total mass or the formula mass for that given compound. And then for each element, you divide its total mass by the mass of the entire formula. And that will give you the percent of that element for that given compound. Since it's a percentage, what we're going to get when we divide those two will be a decimal value. To put it into a percentage, simply multiply by 100 or move the decimal point 2 places to the right. If we take sodium chloride, table salt, as an example, first off, we need to break down what elements are present, how many of each, and the atomic masses for each one that we're going to use. We have one sodium atom with a mass of 23.0 and one chlorine atom with a mass of 35.5. Sum total, the formula mass, is 58.5 atomic mass units. And so if we want to know the percent of sodium, we need to divide the mass of the sodium by itself, divide that by the mass of the sodium chloride, the entire compound. So we have 23.0 divided by 58.5, multiply by 100 to give us the percentage, and we get 39.3% sodium. So almost 40% of the mass of table salt comes from the sodium that makes it up. Now you can, knowing what you know about percentages, get a pretty good idea of what the percent chlorine should be by simply subtracting the 39.3 from 100. But you can also solve the same way that we did for the sodium. Take the mass of the chlorine, 35.5, divided by the mass of the sodium chloride, 58.5, and you would come up with 60.7%. If we take a slightly larger compound, in terms of number of atoms, the same process applies. Here we have the formula for ethanol, grain alcohol, and the formula C2H5OH. We need to find the percent carbon, the percent hydrogen, and the percent oxygen. And so you see the breakdown of the formula mass calculation and the 3 individual elements' contributions to those. So this is yet another reason why showing your work, even for the simplest of calculations, the formula mass calculations, can be beneficial, because in the end we are going to use each of those individual elements' masses. So for the percent carbon, take the mass of the carbon, which was 24.0, and divide it by the mass of the ethanol, which comes out to 46.1, and we find that carbon makes up over half of the mass of the entire molecule. Even though there's only 2 atoms compared to the 6 of hydrogen and the 1 of oxygen, it makes up over half of the mass of this compound. Hydrogen's the most numerous. There are 6 of them, but hydrogen is also the lightest element of all. So those 6 hydrogen atoms only weigh in or have a mass of 6.06 atomic mass units divided by the total mass, 46.1, gives us a percentage of just over 13%. And finally, oxygen 16.0 as a proportion of the 46.1, the entire formula mass, comes up to be 34.7%. So again, quantifying these ratios can be useful because if we analyze an unknown sample and we can break it down into the different elements that make it up and we can determine what these percent abundances are, we can use that to help us at the very least narrow down a potential identification for that unknown compound. Another area where percent composition can be useful is, say for instance, you are in the mining industry, specifically metals, and you're looking for a particular metal, be it copper or iron or manganese or any other metal that might be mined and then purified. Most of those metals are going to be found in the Earth's crust as oxides or as minerals. And so they will need to be chemically treated so that the metal that you're interested in can be extracted. Well, from an economic standpoint, whatever mineral you're going to be mining, you want it to be a very high percentage of the desired metal that you're trying to get out. A, it's more profit, but B, it means less waste. So to determine that, we need to know in a given compound, for a given amount that we extract from the ground, what percent of that is actually going to be usable. And so in the example that we see here, we'll just take a common substance, sodium chloride. We already know that it's 39.3% sodium, 60.7% chlorine. If we had 55 grams of sodium chloride total, we can very easily calculate how many grams of sodium we would be able to extract from that. To do that, we take our percent of the element, sodium in this case, remember to convert it to a decimal, so 0.393, and then times the mass of the entire compound that you have. Essentially, it's a rearrangement of your percentage calculation that we just worked with. So 0.393 times 55 grams, and from that 55 gram sample we would be able to extract 19.7 grams of sodium.